All right, hello again, welcome. A little different format here. We're gonna get all educational here today. Several people in the Crimson Guitars chat, as well as Ben himself, have been asking for me to do a video on electronics for a long time. And today's the day, I guess. We're gonna get started on that. So we're gonna talk. Hi. Don't mind my assistance here. You're not being helpful at all. This is Link. Dude, you're not being helpful at all. Can you go elsewhere?
Link.
So anyway, we're going to talk about several of the components that go into the guitar. Everything from the jack to potentiometers, capacitors, switches, etc. I'm not going to get into super niche type things, roto splits or treble bleeds and things like that. I'm hoping most of what I tell you here today is going to give you a bit of an understanding to seeing how those things work. I might get into a treble bleed. We'll see what happens here. Let's start out small and blow it out of proportion. That's what we do, right? I think that's the motto of guitar builders. Start out basic and then blow it out of proportion. So anyway, starting out, I want to talk about a little bit of basic electrical theory here, okay? I'm going to try and keep this as elementary as possible. I don't want to use a whole bunch of big words and big terms and stuff like that and just have your brain like fuzz out and next thing you know you're staring at your cell phone instead of what I'm talking about here. But there are a few fundamental basics that we've got to cover before we start out. And the first one that we're going to want to talk about is basic circuitry. Anytime we're doing a circuit, any kind of circuit, we have to have a complete circuit. Think of a circuit like a circle, okay? If that circle is broken in any way, I can't complete the revolution. There's a break in the circle, I can't complete the revolution. In electrical circuitry, we're very similar. I have to have a complete circuit in order for the circuit to function. That's essentially the purpose of a switch. Okay, so a basic circuit. A basic circuit is gotta be a complete circuit. Like I said, think about it like a circle, okay? I have a circle. If I have a break in the circle, I can't complete the revolution of the circle. Electrical circuitry is very similar. I have to have a complete path. If I have a break in the path in my circuit doesn't function. Think about your standard light switch circuit. Okay, so I've got my power, circuit breaker, whatever it is, whatever my power supply begins. I have a switch. I have my circuit completes itself back to the source, back to the panel, goes to ground, etc. Okay, I have a complete circuit right now, switch is closed, light turns on. If I open that switch, the light shuts off because I don't have a complete circuit anymore. I didn't lose power. I mean, there's still power here. Unless I go shut the breaker off, there's still power at the switch. Anyway, remember, at this point the light doesn't function. I may have power there, but the light doesn't function. I close the switch, I have a complete circuit, the light functions. Okay? So, when we think about electrical, we have to have a complete circuit. When we think about signal, we have to have a complete circuit. So, in our guitars, our guitar circuit, we start out with the guitar jack. We start out with the guitar jack. Now, we have essentially two types of guitar jacks. Okay, the first one, the one that most of us use, is the mono jack. Okay, now the mono jack has two pieces. If you look at that, first off, we have the barrel, and second off, we have the tip. Okay, just like I have it drawn here. We have the barrel and we have the tip. Typically, how we wire this is the ground and the tip is hot. Okay? So coming from the amplifier, it comes in on the hot, runs through our guitar circuitry, and returns on the ground. Okay. In stereo, there's a little bit more to it because we have two paths and the ground sleeve. So stereo, I've got ground, and then this may be left hot, and this may be right hot. Okay, you know, you think about stereo versus mono music, right? Mono, you listen to it on one speaker and you hear the whole album. You listen to an album that's stereo with only one speaker and you only hear half of the song because the other half of it isn't there because it's supposed to be coming in on the other speaker. Okay, so mono, we have one signal path. Stereo, we may have two. That's not the only purpose of stereo. Sometimes when you have a guitar circuit that requires a dedicated ground for an electronics circuit, you may have a stereo jack on that, and one part is the electronics ground and one part is the electrical circuit ground. Which sounds weird because it's all electronics, right? But I'm talking about a powered electronic circuit within the guitar. B.C. Rich was notorious for this back in the 70s and the 80s when you saw the Mockingbirds and the Bitches and the Warlocks that just looked like a frickin' aircraft dashboard with all the knobs and switches on them and stuff. Typically, they had an active electronic preset for the multi-stage switch to get a bunch of different electronic effects out of it. So you could get more treble, you could get more bass, things like that. That active electronic component there had a 9-volt battery associated with it, but it also required its own ground. If you just tied the grounds together, you'd typically end up with what was called a signal loop, and you'd get this horrible, screechy feedback off of it, okay? We're probably not going to spend a lot of time talking about stereo today. I just wanted to elaborate the difference between the two here. So we're dealing with mono with most of our guitars. That's what we're working with here. Now, your mono jack, if you look at your mono jack, you see two individual posts here for soldering onto. Okay? And those two individual posts, one of them is the sleeve. Okay, so that's the center part here that the jack slides into. And one of them is soldered to the tip, which is this hooked piece here that when I put a jack into it, that's touching the tip and the barrel is up against the sleeve. So I have the sleeve around the barrel of the jack and the tip is making contact with the hot point on the cord. Okay, so we have a completed circuit there. Because like I said, coming from the guitar amplifier, it's coming in on the hot, it's going back on the ground. So this right here, this simple little component is essential for the whole circuit of our guitar. Without this, nothing will work. That's also why it only takes a little bit of corrosion here or a little bit of guck in the sleeve of your jack from playing in a bunch of smoky bars and stuff like that to start getting that thing where if this jiggles a little bit, you get that noise, you know, because this has to be a good durable connection. If I don't have a good durable connection there, everything goes to pot. It all goes downhill in a handcart real fast, okay? So there's our jack. That's where the circuit begins. The next thing I wanted to talk about is the potentiometer. Now, looking at the back side of your potentiometer, you have 3 lugs on your potentiometer.
Can you slide the whiteboard that way just a little?
Not really.
Because there's the light is like there. That's a little better.
Okay. So you have 3 lugs on your potentiometer. And your potentiometer is essentially nothing more than a variable resistor. What's happening here, if you were to look inside of here, you have a resistor inside of that potentiometer, okay? From the left post to the right post, your potentiometer will maintain its resistance all the way across the spectrum. I don't know if you can bring the camera over here so you can see my meter. Tell me when you can read that. Maybe if I need to tip it up like that so you can read it a little better.
Actually, that
Made it worse?
yeah.
You read it?
It says 101.
Oh, it says OL.
Okay.
All right. So, this is a 500K ohm resistor. So this is reading in meg ohms right now, so you can see we're getting about 485,000. That's probably within the tolerance of this resistor. But if I rotate it all the way up or rotate it all the way back, the value of the resistance doesn't change. I'm between the left pot or the left post and the right post, right? That is the full spectrum of the resistor inside that. Is in this case 487,000 ohms of resistance. Okay, it doesn't change right now. What makes it change is the center post. All right. If you can look at the whiteboard here again. Can you see that okay?
Yeah. It just looks like there's the light is, but you can see it. That's better.
Okay. So, the center post is the key element here. Internally, the center post is connected to my knob in the center of my potentiometer. What's going on here is I have what's called a wiper in here. And that wiper slides along this resistor as I turn it up and turn it down. So if I turn this up, this will carry this direction. So now I'll have more resistance from the center point to here. If I turn my knob this direction, I'll have more resistance from my center point to here and less resistance from my center point to here. So this is connected internally to here. All right? So come back here a second and take a look at this. So my potentiometer is still clipped to the one side here, and I'm going to put my other meter probe on the center post and watch what happens. If I turn it all the way one direction,
Oh, hold on.
okay,
Okay, if you turn it.
if I turn it all the way one direction, I have the full resistance. If I turn it the other direction, I have no resistance. Okay? One direction, total resistance. The other direction, no resistance. And if I were to switch this clip over to the other side, get in there. There we go. I would get the same effect in the opposite direction. So right now I have total resistance, and if I spin it the other way, I have zero resistance. And spin it back this way, maximum resistance in the potentiometer again. I spin it back the other way, no resistance. Okay, so looking at the whiteboard here again, essentially what we have done is we have created two parallel resistances. Now, without getting too into series parallel circuits and stuff like that and the rules of volts and ohms and amps and power in parallel, essentially electricity's lazy. It sounds funny to say it that way, but it's true. Electricity is lazy. It always takes the path of least resistance. It doesn't want to have to do more work than it needs to complete its job. It takes the easiest path. Okay? So what happens here, if I have my meter all the way over here, if my entire resistance here is a 500k ohm, all right, if I have this set over to here and I have my wiring between these 2 points, when I turn the knob this way, I have less resistance here and I have more resistance here. So what it essentially means is now I may have turned this all the way to the left, and I now have 0 ohms of resistance on the resistor on this side, and I have 500k ohms of resistance. So less resistance to that point, more resistance to this point. If I turn the knob back this direction, the opposite will happen. I'll have now I will have 0 ohms of resistance from this point to here, and I'll have 500k ohms of resistance to that from this point to there. If I set it somewhere in the middle, I'll have partial resistance on either side. Why is this a big deal? Why does this matter? Well, when you think about how we typically solder a volume knob, we solder one of these posts to the chassis, right? And then that, in turn, connects back to ground. It's my earth signal, it connects back to ground, right? So essentially, if I turn, and then what I have typically is my pickup coming in there, and then this one's probably going out to my tone signal or to my switch. Okay, so what's essentially going on here, as I turn this direction, I have less resistance. That was not tone, I'm sorry. My bad. This is coming in from the switch. Okay, so what's happening here now, if I turn this towards the pickup, I have less resistance in my signal chain going through the pickup. I hear the pickup, whatever the pickup's picking up. If I turn it the other way, the signal goes to ground. Why? Because electricity is lazy and it wants to take the path of least resistance. So if I turn it this way, I have less resistance to ground, more resistance for the electronic signal, and signal goes to earth and I hear nothing. I turn it the other way, it's got to function with the pickup in place. So this is essentially a variable resistor that gives me that effect. If I have two resistances in parallel, if I have a great amount of resistance here and a small amount of resistance here, the majority of the signal is going to go this way. If I have a great amount of resistance here and a minimal amount of resistance here, the majority of the signal is going to go this way. If I have maximum resistance here and negligible resistance here, all the signals going that direction. Okay, so if I set my knob in the center and I have some signal going here and some signal going here, what's going to happen is part of my signal is going to bleed to ground and part of my signal is going to go through the signal chain back through the amplifier and I'll hear that. So as I have that potentiometer set in the center, I have bled some of the signal to ground and some of the signal is still traveling through the circuitry of the guitar. So you turn the volume down essentially, okay? Okay, so the next thing I wanted to discuss here is capacitors. Now, this could get a little tricky, me talking about capacitors without having to get into capacitive reactance and VARs and all that kind of stuff. I'm going to try and dummy it down, elementary school explanation of what capacitors do, okay? Basically, a capacitor that's the drawing for capacitor. You may have seen it on your meters and things like that in the past and things like that, okay? Essentially what a capacitor is you have two conductive plates that are separated by some sort of an insulative material, okay? Most of our dry type ceramic capacitors, or even our paper capacitors, what you essentially have is you have two conductive foils that are separated by a paper or by a ceramic material or something like that, and then they're coated in an overall outer jacket that keeps them contained. Essentially what happens is, with a capacitor, I will be inducing voltage, signal, something coming in on this side of the capacitor. Now, it's not, that insulation is not a perfect insulator. There is no such thing as a perfect insulator. You apply enough voltage to anything and we can make it conduct. Okay, there's no such thing as a perfect insulator. But when we're talking about paper or a thin film of oil-soaked cloth or something like that that's typically used as an insulator inside of a capacitor, what essentially happens is we get a bleed through of electrons. It's not a lot, but we get a bleed through. So what happens here is I've got all these positively charged electrons here on this side, and we will see a few of them bleed through to the other side. Now it's going to be a far smaller value that's making it through here. In electricity, we use capacitors to clean up dirty power. Your sine wave, okay, I'm trying not to get too far ahead of you here with electrical, but when you think of the sine wave has a pure wave form. What happens when we have a lot of harmonic loads? Harmonic loads create unnatural frequencies in the sine wave. So what happens essentially is your sine wave may look more like this, okay? If you were to put an oscilloscope on it, it gets very, what we call dirty power. It gets an impure sine wave. What happens with this is a utility company can't actually tell how much power you're consuming. They get a guess, okay? And they don't like that. They like getting their money out of the people who are using their power. Dirty power can cause you to get fined by the utility company and stuff like that, where they will get really uptight about this. Well, a capacitor will help to clean up that waveform. Okay, it's what we call capacitive reactance, and it's how we improve power factor. That's how capacitors are used in power. We're not using them for power. Okay, in guitar, electronics, and stuff like that, you know, we're not using them to clean up 480 dirty power or anything like that. Okay, what are we using them for? Essentially, what they do with signal is they will cut the high frequency. So when you think about this, if this was a signal wave, an audio signal wave, essentially what a capacitor is doing in an audio signal wave is it's going to cut down the high frequency points. So when you've got a capacitor in your tone circuit, right? And you roll your tone back so your signal's going through the capacitor, and what happens? All of a sudden your tone gets darker, gets muddier, right? Gets that warmer sound to it. Because you're running the signal through the capacitor starts shaving off the high frequencies essentially. So what's getting through here is the lower frequencies in the audio chain, in the audio signal that are more audible, you know, but the higher frequencies get bled off by the capacitor. So what's going to happen here is, depending on the capacitor you're using, your signal may get a slight amount of audio burn off, right? A slight amount of trim, and you may get an incredible amount of trim. Okay, you can get, you know, super muddy, like, you know, southern stoner rock mud, right? I mean, really dark, muddy sound. Your capacitors are sized in picofarads, and I know there's a lot of people out there who are going to be like, no, they're sized in microfarads because every time I order them, they're sized in microfarad. No, they're not. Capacitors are sized in picofarads. They're typically sold with a microfarad value to them. But the number that you read on your capacitor is a picofarad value. And I'll show you how this works. So typically you'll see something on your capacitor that'll say okay, 233J. What is that? That's not the shipping code or the product code or something like that. That's actually the capacitive value of your capacitor. How to read a capacitor. The first number is that number. Easy enough, right? So your first number is that value. Your second number is that value. And your third number is that amount of zeros. Okay? So you've got 23,000 picofarads, which would be 23 nanofarads, which would be 0.023 microfarads, which is probably what you see it as when you purchase it online or in the store or something like that. It's not 23 microfarad. It's actually 0.023 micro. So looking at this number right here, it's telling you what it is in picofarads. When we translate that to picofarads, then do our adjustment, and I know for some of us Americans, this is a little challenging because we don't get into nano, pico, nano, micro, milli, kilo, mega, giga, tera. We don't typically do that in the United States, right? That's metric. But in the electrical world, we use that also. So this right here is how we size our capacitors. So when you see something that says 0.023 microfarad, you're actually looking at 23 nanofarad or 23,000 picofarads is what you've got. Okay, I think that's about it for capacitance before I lose more of you here because this is just getting too technical way too fast. I'm trying to keep it as simple as possible. Now, on to let me check my cheat sheet here. Okay, we covered jacks, potentiometers, capacitors, a little bit of basic wiring, signal path, grounding and bonding. Okay, I hear this argument way too much in live stream conversations and things like that, and I hear people talking about ground loops. Ground loops are absolutely a real thing, okay? I'm not going to tell you they're not. And signal loops are absolutely a real thing, and I'm not going to tell you they're not. But a lot of people misunderstand what a loop is, okay? I've got this thing grounded. I've got this thing grounded. I've got the ground for my cord, right, back to my jack. Then I've got my ground to my bridge, and I've maybe got ground to the shield of the cavity. And they're like, well, that's creating loops. And it's not. Because everything is tying back to one single point. Your bridge, your pickup, your pot, your shielding is all tied back to one single point, and it has one path for ground to return. Okay? This is what we call bonding. Grounding and bonding are two different things. Grounding is connection to earth. Bonding is tying everything together so it's all at one equivalent potential. Equipotential plane. In power electrical, we make sure everything's bonded together. So if this piece of machinery is bonded and this piece of machinery is not bonded, I touch both of them, there could be potential difference, and I'm going to get lit up because I become the bonding jumper that balances the two out. Static shock occurs because of potential difference. Sloughing around in the dry air in the dead of winter, and you touch the refrigerator and ow, son of, right? You were charged. You were building a static charge around yourself in the dry air. You touched something that was grounded and at a zero potential, and it equalized the potential between the two of you. So bonding creates a situation where we don't get a difference in potential. If I don't have a ground wire going to the bridge, what's going to happen here, as the inductive wave, the magnetic lines of flux around the guitar strings from the pickup, will be inducing a charge onto the bridge. And it's not enough to light you up. Okay, we're not talking about power electrical here. But what does happen is I now have a difference in potential from everything that's at a zero potential in here to this, which could have, 4 volts of potential, 9 volts of potential, something like that. And all of a sudden, you'll hear that frequency through the signal chain. That right? And you touch the right? That's what's happening. It is not bonded properly with the rest of the system. So you touch the strings or you touch the bridge, you're the path to ground that's tying it in with the rest of the circuit. So you ground it out and then it stops buzzing. Every time you stop touching it, it's going to buzz again. So we want everything tied together so there's no potential difference. Potential difference is bad. That's where we get the signal wave. That's where we get the sound from. The unwanted hum. Don't misunderstand ground loops in wiring, in electrical wiring. If I have a building here and I have the main service from the utility. Inside the main service, I will have the ground bar, which will also have the neutral land to it there. The ground will land to it there. It's all bonded together there. Neutral and ground are one thing in this point, and it goes out to earth. And I have a ground rod driven into the earth out here. That is my one path to earth. From this point on, every other panel throughout the circuit or whatever, grounds stay separated from neutrals, and all the grounds must come back to here before they go out to earth. If I have a sub panel out here and I take that sub panel also to a ground rod, what can happen in a fault condition? So I have a circuit in here that has a fault, of an electrical fault there. And that equipment ground in that piece of equipment that just had a fault comes back to here. What can happen here is I can take a portion of the fault to ground here and a portion of the fault back to the main system. So what happens is I get what we call a ground loop. Some of the fault goes back there, some of the fault goes back through here. If this is a local breaker for this sub panel, this may not be a problem, but if this fault is occurring on the main breaker in this panel. So I've got a 2-pole breaker inside of here, and I have a fault that occurs here. That fault's going to have to go back to here. If some of that fault's going to ground here and some of that fault's going back to here, now let's say this is a main lug panel that's being fed from a breaker here. I might not get enough fault current to return on this intended path to cause that breaker to trip. Some of the fault's going to go to earth here, some of the fault's going to go back here and go to earth. If I don't get a good rush of fault current through that device and back on a dedicated ground path, that breaker might not trip. In this case, I have split the potential. Also because of the fact that this is probably less resistance than back to here to ground, I'm not going to get a good full blow here or full blow here. It's going to split out across the two. I might get a little more here than there, but it's typically going to cause me a problem. So this is when we talk about our ground loops, this is what we're talking about. In a signal chain, if I would have my power coming in, ground returning, or let's say hot signal coming in, ground returning, and I have my pickups. By the way, I'm an electrician, not an artist, so, you know, if it doesn't look beautiful, I apologize, but, okay, and I wire up these and these and my bridge, and I have my ground connections as that's grounded together and this is grounded completely separately. Say I'm taking this to ground through a different path entirely, and it's going back to the amplifier on a separate path. If these are not bonded to these, I'll end up with ground loop. I'll end up with signal loop, and it'll be a problem. But we gotta, don't misunderstand when somebody solders the shielding and solders the bridge and solders the chassis of all the pots together and all that, you know, the grounds on the pickups, and they're all connected together, and then they're going back on one single path. That's not a ground loop. That's just bonding equipment together. Okay, pickups. Just a quick little bit on pickups here. Some of you maybe tried this experiment in grade school where you took a nail and you wrap a wire around a nail a whole bunch of times. A ferrous iron nail, not you know, a zinc nail or something like that. It's got to be ferrous metal. You wrap the wire around a nail a whole bunch of times, and then you hook it up to a 9-volt battery, and it magnetizes the nail, right? We created an electromagnet. That's how all electromagnets work. That's how motors work. Three-phase motors, AC motors work because of electrical coils creating a magnetic induction. That's how pickups work. Basically what you have is you have a magnet inside that pickup, and you have your pole pieces, and then we wrap this magnet in this really long, really thin copper winding, right? Now, if I induce a voltage or a signal through that, it magnetizes. Well, you put steel strings on your guitar, and what happens is this magnet is generating a magnetic field. And as your string vibrates, when you pluck it, these waves pick up that vibration and it goes back through the signal. What it's doing essentially is it's disrupting the magnetic wave. That disruption of the magnetic wave is picked up as a signal. And if you've ever played a guitar before, you know if you play the string open, it's got a lot more flop to it, if you will, than if you fret it at the 22nd fret and pluck it. It's vibrating at a much higher frequency up there. That's why it's higher pitched. Higher frequency, higher pitch. Okay? Remember, going back to capacitors, I said it cuts the high point of the frequency off, which then in turn limits the high pitch, right? Okay, so as that frequency vibrates faster, it creates a different pitch than when you pluck it at an open and it's got a much slower vibration, a slower frequency. So this is how a pickup works. It's just an electromagnet. The more windings you have in a pickup, the more resistance that pickup has. The more resistance it has, then the more signal it the more, how do I break this down without getting too technical again? Higher resistance means less current. Higher current means less resistance. If I've got more resistance there, it takes more push to overcome the resistance of the load, which gives you a hotter signal. Also, different magnets are going to give you a hotter signal because different magnets magnetize at a different induction, okay? It takes more to induce the magnetic effect on them to get that stronger signal. So when we're talking about alnico versus ceramic, you get different effects there. Rotary switches and regular switches. Well, a regular switch is pretty easy. I mean, when you look at a regular switch, hang on a second here. I'm just gonna run into the other room and grab a switch quick. So if you look at a regular switch, this is a 3-position switch, and looking at the bottom of that switch, you have these two tabs, you have these two tabs, and you have a thicker, more robust tab in the center there. This tab right here is part of the frame of the switch, so that's your ground point. This tab makes contact when I flip the switch this way. If you look in the center here, if I flip my switch that way, it's making contact with this tab. Okay, see that black piece right there? That's my switch point. And it's not touching this side. Okay, if I flip it the other way, it's making contact with this tab on this side, and it's not touching this side. If I put it in the center, it's touching both tabs. But the other side of each tab is here. So what we typically do with switches like this is we will pinch these 2 points together and solder them together in guitars. So when my switch is in the center point, I have my neck and my bridge pickup going out on signal. If I have my switch only this way, my neck pickup is the only one going out. My bridge pickup is currently isolated. If I switch it the other way, my bridge pickup is going out. My neck pickup is currently isolated because it's not making contact back here. In the center position, both of them will go out on that for that purpose. And of course, the next question I get is, how's a kill switch work? Well, just like the light switch does. Okay, when I was talking earlier with the light switch, if I flip the switch open, it kills the circuit, right? Basically, all a kill switch does, when I flip a kill switch down, it takes the signal straight to ground instead of back through the signal loop. So, no sound. So, on, off, on, off, on, off, on, off, and then you get to do fun things, right? You know, Judas Priest Turbo Lover and that kind of stuff. You get that, right? Anyway. That switches, essentially, it's a analog device in most cases. What about rotary switches, though? Because that's a different scenario entirely. A rotary switch can give me a bunch of different variations, and some of you have maybe played a BC Rich guitar or something like that had that 6-position rotary switch, and it makes the sound different in each position. And how does it do that? Basically, it's utilizing several different capacitors in that system. So you've got and then you still have your switch in the middle, which is going to be main signal coming into that middle point, just kind of very similar to a potentiometer, where you're going to have your internal wiper, where it's going to make contact with this one, this one, this one, this one, this one, or this one. But what we're going to do here, sometimes they're designed this way and in internals, and sometimes you can do it yourself by wiring it externally. But essentially what we have here is we will have several different size capacitors internally. So I might have a, 0.01 microfarad all the way up to 0.044, 0.06 microfarad, and a range of them, and each one of them will give me a different tone frequency or a different tone adjustment and variability. Going back to humbuckers a minute here, one more thing I wanted to discuss. With your standard 2-wire humbucker, essentially what you've got with a 2-wire humbucker is you'll have the outer shield, which is your ground, and then you've got your hot wire, okay? And essentially what has happened is internally, before they finished manufacturing this thing, is they took this coil, soldered it to this coil, and then soldered the leads at the end. So this is one complete wire when it's done. It probably was 2 wires, but they merged them together. So that's a humbucker. It has 2 complete coils connected together, and essentially what happens is, what you've got going on is one signal frequency is running like this, and the other one is wound in reverse. So the other one is doing this. So they're complete mirror opposites of each other. And I know, I'm not the world's best artist. That's not a perfect mirror opposite, but you get what I'm saying. They are constantly working in opposition of each other. A single coil just has this. So that frequency noise that you hear is because you just have that one frequency oscillating, and there's nothing to negate the oscillation that creates the 60 hertz or 50 hertz harmonic noise. What a humbucker does is it operates in direct opposition of the other coil. So it bucks the hum. It knocks out the hum that this wave is creating by making a complete opposite effect at the same time. Okay? Then you get into 4-wire pickups, okay? And a 4-wire pickup, you got black, you've got a red, you've got a green, and you've got a white. I don't have a white Sharpie, so I'm going to use yellow, because white Sharpie doesn't show up very well on a whiteboard. So anyway, yellow's white for the moment. Stick with me here. Okay. So, not all pickup manufacturers use the same colors for the same things. Don't take this as cardinal law. I'm talking about this as it applies to a Seymour Duncan pickup. Okay? If you go to a Bill Lawrence pickup or a DiMarzio pickup or any other manufacturer, this is not cardinal law. This is not ASTM standard. This is just what Seymour Duncan does. So essentially, what you've got here, you've got your hot lead, okay. You've got your shield, which is typically just a bare wire. You've got your red, you've got your green, which is your ground, and you've got your yellow. So what's essentially going to happen here is you have the start and the stop of this coil. You have the start and the stop of this coil. So what happens if I want to have a humbucker? Because this is all multiple wires here. What if I want a humbucker? What I do, I take my white and my red and I solder them together. Okay? If I take my white and my red and I solder them together, I have created a merge between those two coils. Okay? When I created the merge between the two coils, it is now a humbucker. What if I want to be able to split coil? Well, instead of soldering these together, I use these as two separate wires, and I have my start and stop of my north pole and my start and stop of my south pole. So I can run that through a on-on two-position switch and split it out if I wish and get the dual functions of either having it be a single coil pickup or having it be a humbucker pickup. Not all pickups respond well to doing this. Okay, some of them, you don't hear a really spectacular tonal difference in the two. What you really just get is a quieter pickup. It doesn't have as much heat, doesn't have as much output because you're only using half the coil. But it works. Other ones perform amazingly when you split them. You literally get two different types of pickup sounds there. It's really neat. So if we take what we've talked about here now and think about this, I've got my jack, right? And I'm going to draw up the diagram that Seymour Duncan uses. And maybe I don't even need to draw it up. I don't know. You tell me. Can you zoom in on that and see it?
Pretty good.
All right. So there's my jack. So my tip is right here. That's my hot. And that comes up to the center point on my switch. If I flip my switch one direction, that goes out through the neck volume. If I switch my switch the other direction, that goes out through my bridge volume. If I set it to the center, both of them are getting signal at the same time. We're coming in on that center point of the wiper of the potentiometer, right? If I roll this potentiometer all the way this way, I have my ground connection here, and all my grounds go back to earth. If I roll my wiper this direction, I have signal going through my pickup and then back to earth. It's also paralleled off to my tone. And if I use this resistor in parallel, what's going to happen is I have very little resistance through here, comes back through here, down through my tone pot, through the capacitor, if I'm using the capacitor, and then back to earth. Same thing on the neck pickup. Okay, coming into the center point, if I have my knob all the way down, this signal, this side of the signal is going to earth. If I have my wiper all the way this way, this side of the signal is going through the pickup, and it's also coming through the tone pot. If I have the tone pot rolled all the way one direction, then I'm not using the capacitor. If I roll it all the way the other direction, it's coming to earth through the tone and back to ground. And everything that needs to be bonded together is bonded together. Now in this case, they're showing a full ground ring here. I have a ground wire going from the chassis of the switch to the chassis of the neck pot, to the chassis of the bridge volume pot, to the chassis of the bridge tone pot, to the chassis of the neck tone pot. I also have a ground wire that's going to the bridge and the grounds on the bridge pickup and the neck pickup, as well as the end of the south pole of the bridge and the neck pickup, tied to earth, and everything is earthed together and goes back to ground. I have a complete signal chain. And there's no ground loops here, because it's all bonded together and going back to one single path to earth. So that's not a ground loop. There's no ground loop there. Don't use that term. That's not an accurate term in this case. There's a lot more to this. Okay, we're basically covering the generic, the bare bones minimum here. We can get into so many other intricate niche tools, roto splits, treble bleeds, and things like that. We can have push-pull pots. We can have, on-off-on switches, on-on switches. There's a lot of different things we can do with our guitars. And then when we get into actives, then we even go another step. But this is the basics of your guitar electronics. We don't have to make it more complicated. We certainly can. And if you feel feisty and you get into this and you enjoy doing it and stuff like that, shoot for the moon. I did one a while back. Here, I can even get you a picture of it. Hang on a second. It's nuts. It was an old BC Rich bass that I bought. Okay? Now look at this beast. So it's got a volume, it's got a boost volume, it's got a tone pot, it had that roto switch with a Veritone booster circuit board, it had a on-off or an on-on switch to either feed through the boost system or just go direct, 2 DiMarzio pickups that could be split. I could have a coil reverse on one of them. It had your 3-way switch there, and this one did require the stereo jack, because one of the a ground has got to be connected separately that doesn't go through the electronics circuit just to ground everything together as one point. This thing was a monster to wire up. Okay? I mean, I enjoy doing electronics, and I was disgusted by the time I was done with this. But, you know, you can make it as easy or as complex as you want to. But have fun with it. If you don't like doing electronics and all that kind of crap and stuff like that in a guitar, there is absolutely no rule on earth that says you've got to have 2 volume, 2 tone, 2 humbucker, 3-way switch on your guitar. Put 1 pickup in, put a volume knob on it, and go for it. Heck, there's a guy I used to play with. He had a guitar, didn't even have a knob on it. You plugged it in and it was straight hot through the pickup, and that was it. The only volume control he had was a pedal on the floor. You know, you could do as much or as little as you want. You know, so I encourage you to play with it a little bit, mess around, find out what works for you, what doesn't work for you, and start small and build up. Don't decide to tackle something ridiculous tomorrow morning if you're not familiar with this. In the future here, I might do a brief tutorial on soldering too. It's kind of surprising to me that there's a lot of guys who don't particularly solder well or know how to solder even, have never done it before. But you know, I guess it's because I've been doing it for so many years. But I've even had guys that'll ask me how to change strings on guitars and how to balance Floyd Roses and stuff like that. So who knows, maybe I'll do a couple of tutorial videos here in the future that get into some of that stuff too. But this one has been asked for a while on how electronics work and things like that. So that's really what I wanted to get done here. I promised Rab Knox that I'd do it for his Christmas present this year. So Merry Christmas to Scotland from the USA, and and to the rest of you too. I hope you have a happy, healthy Merry Christmas and a safe and wonderful New Year. And I will see you again. Take care.